Today we're gonna compare these two numbers, 2 to the power of pi and pi to the power of 2, and see which number is larger, which number is smaller. Previously I had a video where I compared 2 to the power of square root of 3 and 3 to the power of square root of 2. Today we're gonna follow a similar way when we're gonna compare these two numbers, although this comparison is somewhat more difficult. But we again gonna use two ways. One way is to use algebra and use estimates, and the second way is we're gonna use calculus. But in both ways we're gonna use a concept of monotonicity of functions. So if you're not familiar with monotonicity, I highly recommend you to watch this video, and I posted the link here. And after that, come back to watch this one. So what can we do here? The biggest problem we have here is pi. Pi is an irrational number. So we need to put some kind of estimate on that number. We know that pi is about 3.14. So let's first do some kind of rough estimate. We're going to say that pi is between 3 and 4. Well, now what we're going to do to get the estimate of the left-hand side, we're going to apply an exponential function, 2 to the power of x, to all these numbers. And since 2 to the power of x is monotonically increasing function, inequality is going to stay the same. Now, 2 to the power of 3 is 8, 2 to the power of 4 is 16, so we get an estimate on 2 to the power of pi. In a similar way, we can estimate pi square. We just take this inequality and square it. We can do it because square function is monotonically increasing function as long as the argument is positive. So that's what we're going to get. And again, we got pi squares between 9 and 16. Notice this rough estimate doesn't really help us because these ranges, range for 2 to the power of pi and pi square, are overlapping. We want to find the ranges which do not overlap. In this case, we can clearly say which number is larger, which number is small. To do that, let's get a little bit better estimate on pi. Since pi is about 3.14, we can say that pi is between 3.1 and 3.2. We're going to apply 2 to the power of x function to all these numbers. Inequality will hold because 2 to the power of x is monotonically increasing function. And in a similar way, we're going to square these numbers to get an estimate for pi squared. We know that 3.1 squared is 9.61 and 3.2 squared is 9.92. If you're not sure about that, you can just calculate it on paper. The other thing we're going to do here, we don't really want to deal with this 1 here. We just say, well, I don't really care about 9.61. I'm just going to say that pi squared is less than 9.6. I can always do that. And it's an easy number to deal with. The next thing we're going to do, we're going to look at what we have here. And what we have here is we can split 3.1 as 3 plus 0.1. And then we're going to split it like this, because we can use a formula like this. A to the power of b times a to the power of c equals a to the power of b plus c. It's a property of exponential functions. And what we next gonna do, we'll try to estimate this number and this number. That's what we're gonna do first. What we have on the left is 2 to the power of 3, which is 8, times 2 to the power of 0.2. And we're gonna compare that number with number 9.6. We're gonna divide both of these numbers by 8. We can do that because when we divide numbers by a positive number, whatever inequality we had here, the same inequality we're going to have after the division. And after the division, we're going to get 2 to the power of 0.2 on the left and 1.2 on the right. The next thing we're going to do, we're going to apply a power function, x to the fifth power, to both of these numbers. X to the fifth power is monotonically increasing function, so inequality is going to be preserved. Now notice that a to the power of b to the power of c is a to the power of b times c. We can apply this formula on the left, and we get 2 to the power of 0.2 times 5, which is 1. So what we have on the left is 2. What we have on the right is an application of binomial theorem. Binomial theorem is a formula that allows us to deal with the formulas like this, a plus b to the power of n, and quickly write it out, quickly open the parentheses. And another thing that helps us in binomial theorem is something called Pascal triangle. Now, if you're not familiar with those things, I highly recommend you to go and look what it is. It's very helpful in many, many problems. I also have a previous problem where I use binomial theorem and Pascal triangle myself, and I posted a link to that problem. But what we need to know here is how to deal with a plus b to the fifth power. It turned out that we can write it out this way. And again, if you try to do it manually, take a plus b and multiply by a plus b, multiply by a plus b, and so on 5 times, eventually you're going to get this formula, but binomial theorem and Pascal's triangle make this work much, much easier. What I'm going to do now is I'm going to apply this formula right here. In my case, a is 1, b is 0.2. A to the fifth is 1. The second term is this guy. And then we have a bunch of other terms. We have these 4 terms. Before we're going to write them out, let's just first think what we have here. Notice that the second term is 1. So I have 1 plus some other stuff, right? But notice, what I have here is 2 plus something positive, which is definitely greater than 2. And that's what I have here. So I establish that what I have on the left is smaller than what I have on the right. But if I have less than sign here, it means that I have less than sign here, I have the same sign here, I have the same sign here, and I have the same sign here. And what I found that 2 to the power of pi is less than pi squared. And that's it. Now let's do the same thing using calculus. First of all, we're going to apply a natural logarithm to both of these numbers. Since natural logarithm is monotonically increasing function, whatever the relationship we had here, less than or greater than, the same relationship we're going to have here. The next thing I'm going to do, I'm going to apply this formula for the logarithms that allow us to pull out the exponent out of the logarithm. And if I do that, that's what I'm going to have. And now I'm going to divide both of these numbers by 2 and by pi. And again, since I'm dividing by a positive number, inequality holds. But after that division, this is what I'm going to get. And now I'm going to introduce the function log x divided by x. And we see that what we have on the left is the value of this function when x equals to 2. On the right, we have value of the f when x equals to pi. So now what we want to do, we want to find how the function behaves when we move from 2 to pi. And to do that, we'll take derivatives. To simplify derivative calculation, we're going to assume that f is the product of function g and function h, where g is logarithm x and h is 1 over x. In this case, derivative of f is derivative of a product of 2 functions. And we know the formula how to calculate that. It's a derivative of g times h plus derivative of h times g. Derivative of g is 1 over x, derivative of h is minus 1 over x squared, because h is a power function. Now if we combine all these guys together in this formula, we get that derivative of function f is this. What we need to know is where this function is less than 0, greater than 0, and 0. Notice that 1 over x squared is positive when x is positive. So the sign of this derivative is defined by this parenthesis. But what do we have in parentheses? In parentheses, we have minus log x plus 1. Remember, log x is monotonically increasing function. I am multiplying it by minus 1, by a negative number. That makes the function monotonically decreasing. And then I'm adding 1, which doesn't do anything to monotonicity. So what we have inside is monotonically decreasing function. And that function, we know if it achieves 0 anywhere, it's going to do it only once. To the left of that point, the function is going to be positive. To the right of that point, the function is going to be negative. So the point where we achieve 0, it's this x star. It's easy to see that point is E. E is about 2.7, but for our estimate, what we need to have is that E is between 2 and 3. So now let's get our number line, and this is E on that number line. As I said before, to the left of E, derivative is going to be positive. To the right of E, derivative is going to be negative. Positive derivative corresponds to increasing function. Negative derivative corresponds to decreasing function. But what happens now, and that's where we have a problem or difficulty compared to the previous problem we had, is that 2 and pi lay on different sides of point E. And direct comparison between f of 2 and f of pi is really impossible, because from 2 to E the function is increasing, from E to pi is decreasing, and it's not really clear where we end up here compared to where we started here. And the real trick here is to notice that log 2 over 2 is the same as log 4 over 4. So the value of the function when x equals to 2 is the same as the value of function when x equals to 4. But now we can directly compare pi and 4. We see that when we go from pi to 4, function is decreasing, which means that f of 4 is less than f of pi. And that tells us that f of 2 is less than f of pi. But that means that what we have here is less than what we have here. The same sign is going to be here, here, and here. And we prove that 2 to the power of pi is less than pi to the power of 2.